Hello, everyone. My name is David Moore. I'm Senior Director of Wi-Fi Business Acceleration at Cambium. I will get started in another, let's say, 2 minutes to give everybody time to finish logging into the system. But for now, just hold on. One more minute and we'll get started. Okay, let's go ahead and get started. Thank you, everybody, for joining. If you have questions, please go ahead and type them in. I will answer them as I can throughout the presentation. I want to let you know that this topic, best practices for planning Wi-Fi connectivity, is a very large one. It's one that if we wanted to cover it fully, could take days. So what I've done is to try to break this down into 2 different sets of topics. One is, in general, what are the best practices for approaching Wi-Fi planning, for developing a plan? And the other one is more specific, and it deals with Cambium configurations for the enterprise grade product line. So you'll have samples of both, in general what to do and specific what to do when it comes to Cambium. Okay, so when you're planning a Wi-Fi design, the number one question you'll always have to answer is coverage versus capacity. I know this is, for some of you, this is basic, but it's always good to fall back on this one and answer this question first. Is the purpose of the network one that has to be designed for coverage only, or is it for capacity needs? And the answer will help determine not just where you place the APs and how many APs, but what kinds of APs you need. Examples of this would be a warehouse. If you need coverage in a warehouse for equipment, scanners, for example, to be used, then it is an issue of coverage. So you want to make certain you've got all areas covered well, but you don't need to plan for a large number of devices. On the other hand, if you're planning for a school, you're talking about a large number of devices in a small area. So you end up planning for capacity, and planning for that capacity gives you the coverage that you need. So you don't have to worry about coverage at all if you're planning for capacity in that case. The second question to answer is, what kind of client devices will be used in the network? So understanding those devices themselves help you understand what the limitations are, what the needs are. For example, if it is a school, once again, and everybody has a laptop, then you can assume that you have fairly high-end devices, which means that they can make use of multiple streams on the devices themselves in order to be able to pull down more throughput than, say, a smartphone could or a tablet could. On the other hand, if the devices are medical devices and they're low power devices so they can save battery life, that means that their reach back to the AP, for the AP to be able to hear the clients, will be much reduced. That means you have to plan for better signal strength in all locations. If they're all one-by-one devices, then you know that they're going to pull more of a demand off the AP because the AP won't be able to send at higher data rates than if they're higher end 2x2 or 3x3 devices. And then the third thing to answer is the applications. So all three of these questions need to be asked in every single design that you work towards, that you try to build out. The applications help you define what is the traffic flow. If it's simple email and web browsing, that's fairly sporadic traffic. It's not high use traffic. And being sporadic is a good thing because statistically, you're not going to have everybody on at the same time. Even if you have a large number of devices connected up, you know that their use of the network is going to be spaced out so that you can handle a larger number of devices than if they were all video streaming on the other hand. In the other case, if they're all video streaming, they're at a concert, everybody's got their phone up, they're taking a picture of they're filming the stage and they're trying to stream it out to their friends. That's a lot of upload traffic and it's all happening at the same time. So it's a lot more demanding on the network. Downstream traffic is always easier because the AP controls that. Upstream traffic is always more difficult. So if we know more about the network, such as there are a lot of client-server applications, SAP type applications, R3, then the server back in the core of the network sets the pace. And because it sets the pace and it's on the wired side of the APs get to set the pace for communications with the clients. That means you can handle a much higher capacity of users per AP than if you had a peer-to-peer network where everybody's talking to each other across the wireless network. A peer-to-peer network is very demanding, requires more APs to handle the same number of devices as a client-server type network. Multicast applications, they need special considerations. Multicast always has to be sent at a lower data rate than what the clients can possibly receive at, because multicast doesn't have any type of acknowledgement. So the access point doesn't know if the clients receive that traffic. And as such, the safest way to handle that is for the traffic to be sent at a lower data rate. Now, we can affect what that data rate is by configuration settings in the AP, but you want to make certain that you don't set that so high that you end up with client devices that can't actually understand the traffic that's being sent. And voice over Wi-Fi, probably the most classic example of an application that has to be considered when you're handling design considerations. For example, let's say you're using Wi-Fi handsets that are mobile, so they have battery issues that need to be considered. So they need to be able to save battery life and as such they're not high powered. In order to be able to heard by the AP, you need more APs. Or in order for the AP to hear the client, that is, you need more APs built out in the network. In addition, you're going to probably want to limit the number of channels that are being used. Why is that? Because when the devices need to roam in the 5 gigahertz band in particular, they need to constantly scan in the background for APs to hear what's around. And if they're trying to scan across all 4 5 gigahertz bands, they're not going to be able to do that quickly enough. So if somebody's walking quickly down the hallway, especially in a hospital, for example, where this is used a lot, you'll want them to only limit themselves to maybe 8 to 10 channels. Use the Uni 1 and the Uni 3 channels, for example, not the 2 and 2E. So this will help you to understand how to build out the network itself. Okay, so once you understand those 3 questions, you can move on to the more specific type issues. For example, backhaul in the core network itself. Honestly, most of the complaints that I hear about Wi-Fi are not the fault of the Wi-Fi design. They can be. There are lots of problems with some Wi-Fi designs. There have been problems with specific Wi-Fi products, but most of the time it's something else in the network. It's the backhaul isn't sufficient enough. There aren't enough IP addresses, DNS issues, insufficient MAC tables on switches. This is a great one to think about when you're doing an event. I was at an event in San Francisco. It was one of the largest user events. And they had moved from a Wi-Fi design where all the traffic was tunneled into the core to one where there was local offload onto the switches that the APs were connected to, which should have improved performance, but it actually made it worse because those edge switches could not handle the very large number of MAC addresses that were seen on the network. And it was that network that was poorly designed to handle the traffic, not the wired network, not the wireless network that was causing the issues. But it doesn't matter, because in the end, what happens is Wi-Fi gets the blame. So if you're designing a Wi-Fi network and you want it to work well, you do need to understand the wired side of the network, the core, the backhaul, all the capabilities, the captive portal, for example. If it's a small network, the captive portal doesn't have a lot of demands on it. If it's a very large network, then you might want to consider a high-end captive portal system, say for a stadium, that can handle a large number of devices hitting the captive portal all at the same time. Okay, choosing the AP models. This may sound obvious, but it's worth mentioning. And I've listed a number of things here to consider that will affect which AP models you use. And they're not always the questions or the considerations that people think about right off the top of their head. One of the biggest ones for me is, where can you mount? Are you allowed to mount on the ceiling in a hotel, or does it have to be behind the credenza or under the desk or just not visible? So in that case, you may go from a ceiling mount AP to a wall plate AP. Is it aesthetics? Can you not use an AP that's large? Does it have to be small? Cost versus performance is always an issue. You may have the best design, but if the customer can't afford it, then it's really not worthwhile, is it? And then, of course, more streams mean more capacity. So a 4x4 AP will have more capacity than a 2x2. So if you need that capacity, then you design for that. Focused antennas for very high capacity are always something you should consider. So say an arena, a stadium, a bus station, even some parts of an airport. If you have a large number of users in a small area, you want the AP to not be heard in a very wide area. So what you want to be able to be able to focus on a small enough area with the AP so that you can isolate the APs from each other, avoiding co-channel interference. If too many APs are heard on the same channel, they will slow down communications for each other. So you want to be able to increase that SNR between the AP and the clients. And of course, outdoor versus indoor. And it's not just a matter of, are the APs mounted outside or are they mounted inside, but a matter of what are the environmental conditions. Let's say you are mounting in a building that's not climate controlled, but which goes through large fluctuations in temperature or is very dusty. Then you'll want to use something that is IP67. So it's you want to use an outdoor AP like in a freezer, not an indoor AP. Why do you have to worry about a freezer, even some place that doesn't get too terribly cold, but you might see a lot of condensation? You don't want water inside the AP. And the outdoor AP would protect you from that. So I can't tell you right now which one of these factors is the most important in a design. Understanding the application will help you understand which one of these is the most important and understanding which model AP to use. It will be different at any one point in time depending on the application. Roaming considerations. So in roaming, the most important thing to consider, to design for in roaming is good coverage with overlap between APs. You don't want the coverage, say your application needs a NAIC 67 dBm signal strength or an SNR of at least 15 in order to operate well. You don't want the coverage of one AP to end and the next one to begin right where that border is. You need it to be such that client devices can hear the next AP well enough to be able to make the choice to go ahead and move over to it while it's still able to communicate well with the AP that it's connected to now. So you always want at least 15% overlap in coverage. Depending on the application, it may be more. I like 30%, especially in voice over Wi-Fi deployments, but don't make it too much overlap, because too much overlap means more interference, more code channel interference. So good overlap based on the client that's connecting. So how you measure that is based off of what the device is. Let's say it's a Vocera badge that's very, very low power with a low gain antenna that is held by a lanyard around the neck of somebody who's using it. So you're going to measure that based off of the signal getting through somebody's body. You're going to need a lot more APs for that kind of overlap. If the overlap is for a tablet, then it doesn't need, then the signal strength will be better, or you can hear it better at greater range. If it's for a laptop, even more so. So it depends on the device and the application. A way to also encourage roaming, to encourage devices to move from one AP to the next, is to limit the cell size of each AP. And I don't mean lower the power of the AP. That's actually not a good way to do that. What happens when you lower the power is you do shrink the range over which devices can connect. But more than that, you limit the range at which they can connect at high speed. And that may sound like I'm saying the same thing, but I'm not. What I mean is, at the lowest data rates, at the lowest 11B data rates, especially at 1 meg connections, you can connect still or hear the AP well enough to understand at 1 meg at very long distances, even when you turn the power way down. And you don't want that. You want to be able to define your cell coverage much better by higher data rates. So what I recommend doing is you set a minimum unicast rate. Basically what that does is that tells clients they can only connect if they can communicate at high enough data rates, at whatever the limited data rate is that you're setting. So for 2, 4, and 5 gig, I like setting that at 12 megabits per second. That does two things. That shrinks the cell size for each AP and encourages clients to roam more readily, but it also eliminates any B clients. So if you don't want B clients on the network in 2.4, then you set the minimum data rate to 12 and they can't connect. Of course, there are no B clients in 5 gig. And yes, good point here. Somebody asked, aren't clients responsible for roaming? Absolutely. The only device that chooses when to roam is the client. It's a very good point. But what you can do is you can encourage them to roam by making those changes that I'm talking about. So you can create overlap so they can have the ability to make that decision, and you can set a minimum unicast rate so that they are encouraged to roam more readily. Now, some clients roam very well anyway, you don't have to worry about them. Some clients roam very poorly. They're sticky clients. For the most part, you don't see that as often as you used to. There was a time where any USB-based NIC did not actually understand how to roam. They would connect to the first AP they heard, and they would stay connected to it as long as they could hear it, even if they couldn't actually communicate. And the only way that you could handle this was to force them to disconnect, and hopefully they would hear the first AP they would hear next would be a better one. It's a rough way of handling it, where you force clients to disconnect. Cambium does this. We call it enhanced roaming. You can enable it. I don't recommend enabling it by default, and I'll go through that more details. But if you have to, you can. And what you do is you set a minimum SNR value, where if the clients can't be heard at a certain SNR, then the AP says disconnect. And you hope that they connect to the next best AP. I mentioned before about voice over Wi-Fi devices. Create a smaller channel list for them to scan through. It helps them to do their background scans and hear what APs are present more readily. If they have to do multiple scans before they can pick up all the APs in the area, they may be walking too quickly through an area and might miss their opportunity to roam to a better AP. Okay. So next step, planning. Predictive analysis is a great tool. Something I didn't list in here, but I should mention, even before you do a predictive analysis, if you're going to do one for a network, I would recommend a site survey where you physically go on site or have someone do so that you can understand what APs, where APs can be mounted, where you actually can mount them, and also so you can understand what the RF environment is like. If you can do a spectrum scan, you'll understand better what already exists in the area, and it may not be Wi-Fi. You might have interference from other sources and portions of the spectrum, channels that you cannot use or that you can use. You'll be able to input that information into most predictive analysis tools, such as Backhaul, IBWave, or AirMagnet, where you can set the ambient noise floor, and that will help you when you do your planning. But for any large deployments, this type of tool is invaluable. You really do benefit significantly from it. It is absolutely worth having access to the tool or access to somebody who has the tool. So what they'll do for you, if you haven't used one before, is you can upload a floor plan. CAD files are the best because they give you more information typically on what materials are being used and the walls and the floors, windows, things like that. And you model these obstructions, the walls, the floors, the cubicle areas, the stairwells. You model that, and you can either have the system automatically place APs on the floor plan for you where it thinks they're best placed to include what channels if you want to do a fixed channel plan, or you can place them manually and see what the coverage looks like. So what you see on the picture here is a heat map from Backhaul, and it shows what the signal strength in this case would be seen at different locations based on those APs. But you can do more. You can create areas of capacity planning, or let's say you were handling conference rooms, meeting rooms, a lobby area, and you knew that you were going to have 500-600 devices connected up in an area. You can indicate that area for how many users there will be, how many devices, and the planning tool will help decide how many APs are needed, not just based on number of APs per or clients per AP, but based on a minimum throughput that you require on those APs. And it will take into account the ambient noise floor without the APs, and then the added noise co-channel interference based on how many APs are placed in the area and what channels that they're using. So it's a great tool to use. Also gives you a deliverable, something you can provide to a customer, and something that you can use as the baseline for when you actually do deploy to see if you've missed something. You know, have I forgotten to deploy an AP, or did I not model something correctly? And you can go back and correct that. However, what's really important here is that last point: garbage in, garbage out. If you don't put good information into the model, you're not going to get a good model out of it. If I model all my walls as a 5 dB loss, and they're actually a very thick wet concrete, that's a 12 dB loss, I'm going to underestimate the number of APs. Just as damaging if I model these all as drywall with a 3 dB loss through them, or 2 dB loss, or I'm sorry, if I model them the other way, I model them with too much loss, 12 dB loss, and it's only a 3 dB loss, then I'm going to end up with too many APs, and my performance will actually be worse than it should be. So you do want to plan them well, and one of the best ways to do this is to get an AP on site, measure the signal strength when you're near the AP, and then when you're on the other side of the wall. So you can get a sense of what the loss is through that wall. Verification. So let's say you built it out, you modeled it, you've gone on site, you've deployed the APs, now go out on site and measure the actual performance of the network. Those same tools that did predictive analysis offer site survey tools. There are other site survey tools out there as well. You can even do this with simple Wi-Fi analyzer that you can run on an Android. But it's important that you do this at some point so you have a benchmark to understand what the performance actually is. And if it changes over time, it could be because the number of devices have increased, noise has increased, or the structure has changed. But it gives you something to go by for today and for meeting your service level agreements and for troubleshooting in the future. Okay. So let's talk about channel considerations. Oh, looks like there's a question here that I missed. Let me read through this. If you asked a question about what is the efficient solution for such an application, I only saw the last part of the question. I'm not sure what application you're talking about. So if you could send that again, please let me see it. And somebody asked about don't focus antennas increase the size in a given direction for coverage? Yeah, evidently I'm having a hard time seeing all the questions on the screen here at once. So let me back up here. Somebody asked about focus antennas. It was, I believe, Chetan, increase the size of coverage in a given direction. Absolutely, they do. If you don't do things like down tilt the antenna, what they do is they prevent you from focusing your coverage everywhere, or not focusing at all, but sending out everywhere like an Omni would do. But they do focus in a certain direction, which means it's higher gain, which means you'll reach farther. If you don't down tilt, that's absolutely true. If you do down tilt so that you're limiting yourself with the objects in the area, like the ground, the floor, then directional antenna can give you a much more focused area of coverage, limiting that range. That's what we do with high gain antennas in like a stadium. Use a 30-degree antenna to cover, say, 200 seats at a time. And by also being high gain, you'll get better signal strength to and from the client, which means they can operate at higher speeds. They get on and off the air faster. So that's a good thing. And when we have full duplex Wi-Fi connections, if ever, Wi-Fi itself is not designed for full duplex. We're sharing the medium, the air. Now I say that that you send and then you receive, then you send and then you receive. But let me also point out that 11AC does allow the AP to send to multiple clients at one time. It's multi-user MIMO. 11.AX or Wi-Fi 6 allows for multi-user MIMO in both directions, so multiple clients can talk to the AP at one time. Now, what we're not doing is AP and client talking to each other at the same time. It's a shared medium. I don't picture a time where it's ever going to be full duplex, but I don't know. Maybe somebody will come up with a method of doing this where we use two different channels. But today, that's not the case. And I think that's everything. Okay. So channel considerations. Currently in Wi-Fi, what we have is 2, 4, and 5 gig. I say currently because there are always plans always questions about how can we get more spectrum. You always want more spectrum so you can have more capacity and more options. 2, 4 is better propagation, better penetration through objects. That's good and bad. So if you need to get better penetration, you need to have a signal go farther for more coverage, then 2, 4 is good for you, right? But there are other systems using 2, 4, like Zigbee and Bluetooth, baby monitors, microphone systems that they're used on stages. So you can run into a lot more interference in the 2, 4 band that is fairly narrow, as opposed to the 5 gig band, which has lots of channels to choose from. 2, 4 doesn't. Depending on where you are in the world, you may only have 3 non-overlapping channels or 4 non-overlapping channels. So you're limited in your capacity, but don't ever eliminate 2, 4 from your design options. It's a mistake to do so, unless you have so much interference that it's unusable. It's more spectrum. Make use of more spectrum. Have some clients on 2, 4 and most on 5 gig. That's a good WLAN. That gives you less crowding in the 5 gig space by allowing some of it to offload into 2.4. Now 5 gig, less propagation, less penetration, that's bad and good. The good part is you can isolate the APs from each other and reuse those channels more often. So in a school, for example, you might have enough APs that you'll use all the 5 gigahertz channels more than once. And by using the walls in the school to block signals from each other, that helps you to be able to reuse those frequencies more readily and get more throughput off of each of those channels. However, beware that there are differences in the different bands. Whereas a 2.4 band, it's one small band. The power output possible is the same across that whole band. In the 5 gigahertz band, it's actually 4 different bands. Uni 1, Uni 2, Uni 2 extended, and Uni 3. And depending on where you are in the world, you have different regulations for each of those bands so that you'll get different throughput for different bands possibly. So different countries have different rules so that you might have the same amount of power allowed in different bands than you would in others. Let me see what this question is. Somebody's asking, can we mix 2.4 and 5 gigahertz in APs always? Yes, and sometimes you don't want to. So can you? Yes. Almost every AP out there today, certainly on all of them on the enterprise level side, are dual band at very least. So they're 2.4 and 5 gig at the same time. And there's no reason not to use both on some of the APs. If you have a very high density deployment where you have lots and lots of APs deployed, you will end up with a situation where you have too many 2.4 gigahertz channels enabled if they're all turned on. So, for example, in a stadium, you'll often have every AP using 5 gigahertz and only some fraction of them with the 2.4 radio turned on. So you may turn off some of the 2.4 radios, but you'll want some of them on. Good example in a stadium would be probably no more than a third of the radios with 2.4 gigahertz turned on, maybe only a quarter. DFS channels. So in the Uni 2 and Uni 2 extended bands, we have to abide by DFS rules. If there is actually radar in the area, you're better off not even trying to use those channels. So there are times where those Uni 2 and Uni 2 extended bands are not worth using. Also keep in mind that the Uni 3 bands, Uni 3 band is used quite often for backhauls, for point-to-point and point-to-multipoint, because of it's at least in the US. And the reason for that is the EIRP limitations allow for much higher throughput, or much higher power and a lot higher gain on the antennas. So you can experience significant interference in that Uni 3 band when you're outdoors. Doing a site survey will let you understand whether or not that band is useful to you. Okay, any other questions that I'm missing here? I think that's all of them. Okay. Channel width considerations. Okay, so Wi-Fi allows for 20, 40, 80, even 160 megahertz wide channels, at least in the 5 gig band. And in the 2.4 band, you can do 20 or 40 megahertz wide channels. The truth is, 160 megahertz and 80 megahertz are rarely practical, if ever. Maybe in your home. But I do not recommend ever trying to use either one of them. And the reason why is it's much harder to find a clear channel. You're more likely to have co-channel interference. If you use 20 or 40 megahertz wide channels, honestly, I prefer 20. Then you can get more APs deployed that don't have to compete with each other. This means more capacity. Your biggest limitation for capacity is the AP itself. How many devices can it talk to at once? So if I have one AP that's using up the only 40 megahertz wide portion of the spectrum that's clear. Let's say we have this limited use case, and it can handle 300 clients. We're much better off with 2 APs that can, and let's say we have 400 clients we need to serve. We're much better off with 2 APs at using 20 megahertz wide channels that can then serve a total of 600 clients instead of the limitation of 300 on that 1 AP. It's easier to find a clear channel. There's more power density focused on that smaller channel than if we're in a wider channel, which means we actually have a slightly better range and, like I said, more capacity. Limit the number of WLANs. So this is becoming more and more well known. Didn't used to be well known at all. And for a while there was a move towards using lots and lots of SSIDs. In fact, manufacturers were starting to offer, I know one that can offers 54 SSIDs possible on a single AP. Don't ever do that. You'll never have any airtime left to serve your clients. You want to limit the number of SSIDs that you advertise. 4 is probably a good number to limit to. However, if you have a high density deployment where you have a lot of APs that can hear each other in the same channel, looking at this table, you can see that if 4 APs can hear each other on the same channel with 4 SSIDs, you're already using up more than half of the airtime. And why is this? Because for every SSID, you have a beacon that has to be sent out every, by default, 100 milliseconds that says to all the clients out there, here I am. And it also gives more information, like for clients that are in power save mode that are asleep, it'll tell the ones that need to wake up when they wake up that they have traffic or they don't have traffic bound for them. But anyway, that beacon that's being sent out is sent out at a low data rate. By default, it's sent out at 1 or 2 megabits per second over the air for 2.4, at 6 megabits per second for 5 gig, at the lowest data rates possible. And that's because you want to make certain that all clients can hear it. So by sending more and more beacons out there with more and more SSIDs, you're using up all of your airtime just to say, hello, here I am. You're much better off using fewer SSIDs if possible and separating traffic by VLANs, maybe using dynamic VLANs, using radius to assign that, if you need to separate the traffic more. So let's get into specific settings for the cnPilot products. And before we do, I wanted to go through something on cnMaestro that some people might have missed. That's if you're doing a Wi-Fi only deployment, enterprise Wi-Fi only deployment, there's a setting within cnMaestro that makes it a little easier for you. You can go into under application and settings and account type and choose wireless LAN. So if you're not using any backhaul, any P2P, any point-to-multipoint to manage on your account, you're not doing the R series, then choosing this wireless LAN option gives you a little more intuitive interface for Wi-Fi only. However, if you are doing Wi-Fi or point-to-multipoint, point-to-point products, then you'll want to choose the access and backhaul option. You don't lose any capabilities for Wi-Fi doing this. It just, the placement of where the configuration settings are done will be slightly different, and I'll point that out here. But it's more intuitive if you're only doing Wi-Fi to do it in the wireless LAN settings. So what you'll notice is on the left-hand side is the access and backhaul view. On the right-hand side is the wireless LAN view. And you'll see that where the AP group configuration settings are in different places. Where the WLAN configuration setting are different places. They've been pulled out and separated for the wireless LAN view versus the access and backhaul view. But everything is still there. So when it comes to any specialized or recommended base configurations in 2.4 and 5 gig, where you'll go to is under your AP groups and then the configuration and radio settings. Here's where I recommend making some changes to the configuration. So most of the default settings are great, and you won't have any reason to change them. The options for enable, channel width, transmit power, antenna gain, all that on the 2.4 side are valid, and there's really little reason to change them, although you can, unless you have a specific reason. The one exception might be the enable button. In a highly densely deployed scenario, you will probably want to turn off some of the 2.4 radios, such as a stadium. That's the highest density one I can think of. But the minimum unicast rate is the one I brought up before. That's one where I do recommend changing it from the default of 1. 1 is actually way too low. You end up with this really long tail of coverage where clients can hear the AP and will try to connect, but they can't actually communicate effectively with the AP because they're so low power they have a hard time being heard by the AP. So at a minimum, bring that up to a 2 megabit per second. But if you want to eliminate 11B clients from connecting to the network, bring it all the way up to 12. Because the lowest rate that 11B clients can connect at is 11 meg over the air. So setting it to 12 prevents them from connecting at all. Airtime Fairness is something you should enable also in the 2.4 band. So that's something I want to go into a little more detail. What is Airtime Fairness? What does it do? And why does it make sense to turn it on in the 2.4 band? So if you look at the graph on the right, what you see is an example of 11A and 11N clients, and that could have just as well have been 11G and 11N clients throughput without Airtime Fairness turned on. And you'll see that that green line and that purple line are pretty much they're matching each other on throughput. What's happening here is that 11A or that 11G client is a much slower client, and statistically, the 11G or A client has as many opportunities to communicate with the AP as the 11N client does. And when they do communicate, they communicate at a much lower throughput than the 11N client does, which means they take more time to say the same amount of, to send the same packet. So you've got this device that very quickly passes this information and one that very slowly does. And the one that's quick has to wait for the slow one every time. So it's like you're a fast walker and you're trying to get through the airport. Everybody in front of you is walking slowly. So even when your step goes your one step is very quick, you've got to wait for the person in front of you. It takes tiny little steps to take 2 or 3 to move forward. They set the pace. The slowest client sets the pace and everybody gets thrown back down to it. If there were an 11B client in the network, this is really bad. Everybody's limited to the 11B's throughput. So Airtime Fairness gives everybody, rather than equal number of packets, equal amount of time to talk. And that way, you'll see in the lower graph that the 11N clients are able to operate at a much higher throughput, much closer to what the 11N's capabilities are, while the 11A or 11G clients are still back down where they were in their throughput. This is great for 2.4 because in the 2.4 band today, the only clients that exist are B, G, and N. And why is that important? Because when 11AC came out, 11AC added improvements into efficiencies in communications by adding block acknowledgements, by aggregating traffic. And when that happens, and you limit the amount of time every user has to talk, Airtime Fairness actually can affect 11AC clients detrimentally. It can limit their total throughput. So in the 5 gigahertz band, where most clients are now AC, you're better off not turning Airtime Fairness on in 5 gigahertz in my experience. Turn it on for 2.4, but not in 5 gig. Now, if you had a network in 5 gig that was mainly 11A and 11N clients, turn it on and make sense. If you have a lot of 11AC clients, don't turn it on. Allow that aggregation capabilities built into the protocol to take care of this. It's one of the cases that you get to see where the standards keep improving matters. This problem popped up with Airtime, that Airtime Fairness solved, and then the standards in 11AC addresses it. When 11AX comes out, 11AX will work on 2.4 as well. We'll see that improvement in the 2.4 band too. Okay, now 5 gigahertz specific settings in the radio. So the base settings, which I mentioned before, don't turn on Airtime Fairness unless you only have 11A and 11N clients. And I do suggest upping the minimum unicast rate from 6, which is you'll see on the screen here, to maybe something like 12. And then the next thing to consider is candidate channels. I set this one to specific, and I listed the channels that I would use. In this case, these are all Uni 3 channels. And why did I use those? Because in the environment where this deployment is, the Uni 3 band is fairly clear, and I'm able to operate at higher output power from the AP down to the clients, which means that I can do higher MCS rates down to the clients. So everybody can get higher throughput than if I were also using Uni 1 bands. And there were enough channels here for the APs that were deployed in this network that's fine. So there are times where you'll want to make use of those candidate channels. In fact, if you look here what the options are, you can say all channels are available, prefer non-DFS, prefer DFS, or prefer specific. Prefer non-DFS is probably one of the more common settings. Not all clients understand DFS channels. So if they don't, then you'll want to prefer non-DFS. Or if you're in an area where there is radar, you'll want to avoid that radar and set up for prefer non-DFS. If you are in if you're doing a deployment like a stadium, you'll want to use every channel you possibly can. So you'll probably want to have the DFS channels enabled as well, unless you have radar in the area. Okay. Somebody asked, am I getting your questions? I'm not seeing all the questions, evidently. Here we go. Here's one I missed. What is the best solution of Wi-Fi implementation for offshore platforms? There will be steel structures, concrete walls, etc. So the coverage area will be much less. When we draw the heat map for such areas, it is strange. Yeah, I could see that. If you can properly draw the heat maps, one thing I would suggest, if you have access to either Backhaul or IB Wave, they do a good job of multiple floors if you model the floors properly. So you may or may not have leakage through. My guess is on these platforms you probably don't. So in those cases, you end up with, well, obviously I would suggest outdoor APs for most of the structure. If you don't have indoor areas that are climate controlled, then all outdoor APs. If they are climate controlled indoor, then you can make use of the less expensive indoor ones. Most of those indoor spaces are going to be fairly small, so use a less expensive AP. The capacity needs are going to be less. You don't need something that can handle 300 clients, right? So either like an E410 that's a 2x2 indoor, or maybe a wall plate where you might also make use of the Ethernet ports. You need more APs. You just flat out do when you do coverage like this. But you're right, you get some strange effects from all the metal, from reflection, from multipath. And if you come from a time when every time you had multipath issues, it was detrimental to Wi-Fi, early on in the Wi-Fi days, try to unlearn that, because with 11N especially and 11AC even more so, they both make use of multipath. Multipath is not a bad thing. It helps the clients in the APs to differentiate between the different streams, to decorrelate them. So what that means is, if you get coverage around the corner because of reflections of the signal, you can make use of that. You can still communicate well. So trust those heat maps. If you're doing Backhaul, I am a big fan of Backhaul's abilities to predict well, as well as IB waves. As long as you put the information in accurately, they do a good job. I don't know what else to tell you about that. You want APs that can handle the environment, and you'll need more APs because of it. So if you, a focused antenna, for example, a 120-degree sector or a narrow beam 30-degree antenna on a platform, probably not a good fit because you don't need to go that far. So sticking with omnis is probably your best fit here. You'll just need more of them. And let's see, were there any other questions that I missed? How do you know if there are other APs on the same channel except the network doesn't work efficiently? So tools such as Wi-Fi Analyzer on a smartphone can tell you what APs are out there because they're listening for the beacons. On the APs themselves, on our APs, you can go into the site survey tool to do a spectrum analysis, and it'll tell you what other APs are present. You can also use tools such as Backhaul has a hardware tool called Sidekick that does a very good job of scanning for other APs for ambient noise floor. You'll be able to see what is present in the area. So anything that can be used to scan the network to see what is around, you can tell. Now that doesn't necessarily mean that they're active, that they're very active, that they're going to cause a problem. Because another AP is in the area is not necessarily a problem. It's how active they are, how much airtime they use. Wi-Fi is designed so that if you share a channel, that the APs will play nice with each other. If they're both in the same channel, they'll back off when one will back off when the other one is talking. Now that means less capacity for each AP, but it also means that they're not talking over each other. So it's not a terrible thing when it happens, but you're right, they're not as efficient when that does happen. Let's see, is there something else? What is the best solution for Wi-Fi? Okay, same one we just covered. So I think that's all the questions at this point. Let me move on. So advanced options. So these advanced options on both the 2.4 and 5 gigahertz radios, the settings, I would say for the most part, there's not a real good reason to set them differently from each other. I would use the same settings I'm going to cover next for both 2.4 and for 5 gig. They give you more control over things like automatic channel selection, interference avoidance, how to handle the problematic client devices, sticky clients. Oops. So let's start with automatic channel selection. So on this one, you have three options. You can do no clients on startup or schedule. And what this does is the AP will choose the very best channel that it can go to. It's not looking for a threshold. It's looking for what is the best channel, and it will switch to that channel. And you can either have that only happen when it first starts up. You can have it scheduled to happen once a day, and you tell them what time of day. Or what I prefer is when there are no clients connected. When there are no clients connected, there is no reason not for it to not change. It's not going to interrupt anything by doing so. And the default for that is 6 minutes. I don't see any reason to change that time. You can. That's my favorite setting for this, so that you have the APs automatically switching to the very best channel they can hear every 6 minutes if nobody's connected. That one's kind of non-controversial. The next option is enhanced roaming. And frankly, I kind of wish we didn't call it that because it makes it sound like, it's enhanced. Like, yeah, I should do this, right? Don't do it unless you need to. What this does, it's a harsh method. I mentioned it earlier. It's used for sticky clients. It's used for clients that refuse to roam or roam poorly. They hold on to an AP way too long. They need to switch over to another AP. And what you do here, if you enable it, is you use a threshold and say that if a certain signal to noise ratio is not present for that client being heard by the AP, then the AP will tell the client to disconnect. And then when the client disconnects, the hope is that the client will then choose a better AP. If it doesn't, and it tries to connect to the same AP, and the same AP will then say, sorry, you have to disconnect again because your SNR is still not good enough. So you can see where this can be problematic if you have a really troublesome client. It also makes it easy for you to accidentally set or to create coverage holes where you've got a spot in your network and you're in the area you're trying to cover where you can't get an SNR high enough. That's a problem. So you have to be very careful when you use this. I prefer not to use it unless you need to. And quite frankly, most client devices are good at roaming. It's some of the older clients, some of the Chromecast clients that have trouble roaming, in which case you may need to turn this on. Off-channel scanning. Okay, so this is where the AP has the ability to go offline for brief periods of time, to scan the channels that it's not operating on, and to build a database of information, understanding what other devices are out there and at what signal strength. And what is the ambient noise floor for each of those channels. So this is necessary for it to be able to make an intelligent decision on changing channels when certain thresholds are met. So I do recommend enabling this, and that using the default settings, the ones that are there are good. Let it leave the dwell time, samples, or interval, number of channels that's scanned per time period that it goes off channel. What this does is it's just very brief. It just goes off channel briefly, just scans one channel. The next time it goes to do one, unless you change the number of channels to something higher. I like setting it exactly where it is. And you'll want to use that in conjunction with auto RF and interference avoidance. So let's back up to auto RF. Auto RF, this allows the AP, if it hears other APs in its own network on the same channel at a high enough signal strength, they will both turn themselves down so that they reduce co-channel interference. And if the RF environment changes later so that they don't hear each other that strong, they can turn themselves back up to increase their power as needed. So this allows for high density deployments for the APs to turn themselves down. Now this only works so far, and is why you sometimes end up turning off the 2.4 gigahertz radios in very dense deployments. But this is not something that you should avoid enabling. Go ahead and turn it on, use the default settings in case you run into the condition where multiple APs are on the same channel and they can all hear each other. It will improve performance overall for everybody. Interference avoidance, now in conjunction with OCS, where that database is built up over what other channels look like, where can they go next if they ever need to change channels. This is where the decision is made that if a certain threshold is met, that the AP does need to change channels, that interference conditions are bad enough that the channel that the AP is on is no longer a valid channel and that it should go to the next best one based off that database built from OCS. So enabling this allows that to occur. Now, when that does occur, the AP uses 802.11h, that protocol that will tell all the clients that, yes, he's going to move. So I'm going to change channels. This is the new channel, and here I go. And the clients can then follow to the new channel. Now, this is built into any 5 gigahertz client. They all understand how to do 11H. 2.4 only clients, ones that don't understand, that client devices that also don't do 5 gigahertz, won't necessarily know what 11H is. They won't necessarily understand the message that was sent. However, they are better off realizing the AP is not there and searching for it on the new channel because the channel that it was on was bad enough to warrant a change. So it's still worthwhile having this enabled on both 2.4 and 5 gig. Okay, so let me see. Sorry, I was having trouble finding all the questions. Let's see. Are there any more here that I missed? Doesn't look like it. I think I've got all of them here. Here's one. Here's a channel, or here's a question that I missed earlier. Having 4x4 MIMO benefits. Most advanced client devices are limited to 3x3 MIMOs. So how does 4x4 work? Does it split into 1x1, 2x2, or 3x3? Great question. So what's the benefit of having a 4x4 AP if the highest end client you can find is a 3x3? So what does that mean to have 1x1, 2x2, 3x3, 4x4? One way to look at this is their degrees of freedom. So an AP with multiple streams, or any device with multiple streams, has multiple choices of what it can do with those streams. It can, in a 2x2, for example, it can double up on the data that's sent. Some sent on one stream, sent on the other, and get twice the throughput. Depending on the MCS rates, it might be twice, say 10 meg throughput versus twice 100 meg throughput, but still it's double what the MCS rate was that it can get through. 3x3 can get 3 times. A 4x4 could, but in this case, the client's not 4x4, so what's the benefit here is the question. Well, there are other degrees of freedom. Another one is called MRC, maximal ratio combining, and what that does is it allows the device that's sending or receiving to do so on multiple streams. So the AP can send the exact same data on 2 of those streams. So on a 4x4, it could send some of the data on one, some on the second stream, and then on the third and fourth stream, send the exact same information out. And that information will be better heard by the receiving client, at least on that one stream, by as much as a 3 dB gain by sending it out twice. By doing it on 3 streams, it's a 5.7 dB gain, I believe. And on 4 streams, it's not, it's not 1/4 more as good. It's diminishing returns as you add more and more. Another thing that can be done by a device with multiple streams is it can make use of those, it can send the same data out on multiple streams and send them out slightly out of phase with each other. And what this does is this creates places in space where we have constructive or destructive interference. This is what transmit beamforming does. So it allows us to create antenna patterns with higher gain in some directions and lower in others by making use of these out of phase signals sent on different antennas or in different streams. So an AP can choose to make use of any of these methods or all of these methods or any combination of these methods. By having more streams, it has more capabilities of both hearing and transmitting, even if the client devices that are on the other end don't have as many streams. So that's a fair question. And when we get to 11AX, we'll have 8x8 radios, but we won't have 8x8 clients. In fact, the vast majority of clients will be 1x1 or 2x2. Well, when we start talking about multi-user MIMO, that makes use of that transmit beamforming that I mentioned, where you send things out of phase and you create new antenna patterns. That's what's going to be happening, is we'll be able to talk to multiple 1x1 or multiple 2x2 clients through the use of transmit beamforming to the clients. And then we'll also be able to do it in the upload mode coming from the clients. So it's good for the AP to have more streams than the client does. It does give it more capacity. Let's see. Does the channel 1.6.11 and 2.4 band help with avoiding, using those channels help with avoiding interference? Yes, if you use non-overlapping channels, 1.6 and 11 in the 2.4 band in the US or 1.6, 11 and 14, say in Europe, then those channels don't interfere with each other as long as you're using 20 megahertz wide channels. If other devices out there are using the same channels, we're better off sharing a channel than using ones that overlap, like channels 1 and 2 or 1 and 4. When that happens, any device in Wi-Fi will back off when it hears another device that's using Wi-Fi, and they'll both understand that process. If they're not using Wi-Fi, it will back off if that is heard at a high enough signal strength as interference. But they won't play nice together. They won't have that communications that you would have if they both understood they were Wi-Fi. So you end up with more problems typically when they overlap. That being said, there's some tricks you can play by doing like 1, 4, 7, and 11 with slight overlap, understanding that you're going to have less total capacity per channel, but more overall capacity for all 4 channels. It's a game that if you don't really understand Wi-Fi, you probably don't want to get into it. And I don't have time to go through that here, but it is possible to have non-overlapping channels and improve your capacity if you know what you're doing. Okay, so that one answered. I'm still going through these questions here. How can you review the recording of this session? So the session and the slides, the recording and the slides will be posted online. I don't have the information over exactly where, but Susan, are you online? Can you hear me?
Yes, I can. They will be posted to our YouTube page and our community page. So if anyone has any questions, about the webinar, they can comment on the community.
And how does different SSIDs affect APs per AP affect roaming? Different SSIDs per AP affect roaming. So if you need to roam, if you want roaming capabilities, you want clients to be able to roam from one AP to the next, it has to be on the same AP, same SSID. So you do not want to have different SSIDs per AP unless you want to have different networks that are completely separate from each other. You want each to have the same SSID, the same subnets as well. You want them to share the same broadcast domain. Some clients will send out a GHCP lease renewal when they move from one AP to the next to verify that they haven't changed subnets. Most clients will not. And even those that do, don't typically do so on a consistent basis. So you want them to be able to use that same IP address they got the first time they connected every time they roam. So do not create a network where you have a different SSID on each AP. You want the same one everywhere. Okay. How is it named the YouTube channel? I'm not sure what that means. Let me move on here. How should I consider the bandwidth for meshing in cnPilot? So I didn't cover meshing on purpose. Meshing is not my favorite method. It is a good tool to use when you need to. But using mesh, which is where you have APs that communicate with each other across the wireless network, where at least one AP in the network is not connected via Ethernet. This allows you to extend coverage. It does not give you more capacity because you're limited to that connection between the APs and your total throughput. Another reason I'm not a fan of using it where you don't need to is that the channel that you use on, say, the base AP, that will be the best channel possible based off of RF and interference avoidance, but it may not be the best channel on the client AP, the one on the other side. So that being said, let's say you do use mesh, you have to use mesh, you have a good reason to. One thing that you should be aware of that's different with cnPilot than many other systems, but not all, is that our mesh is WDS. So that means that you do have to tell devices that they're either a base or a client device. So it takes a little more configuration, but you can choose which radio to use. So if you did multiple hop meshing, I can have the first hop be over 5 gigahertz and the second hop be over 2.4 gigahertz. So that means I don't have to use the same channel for every hop. I can flip back and forth. And that means that I can have more overall capacity throughout the network. I'm not having to share that same channel for each hop, so I'm not having my throughput every single hop. But if I keep flopping back and forth and bands, I only have my throughput for the first hop, but not for the second one. So that is important to note, but I advise using mesh with caution no matter whose mesh you use. Let me see here, what else? I have auto RF features that are not configurable from cnMaestro can only be modified on the access point individually. Is there any plan to make these settings part of Maestro so that the central management console is indeed a central management console? Yes, actually, all the RF features are on cnMaestro at this point. You may have noticed on my screen that some of the options have been deprecated. Version 3.6, we took off some of them depending what version of code you're using, and we've added some. So you may be looking at options like packet drops and radio errors that are no longer showing up in the new code. So if the code running on your AP is newer, it might have different options, but they're all there on cnMaestro. It truly is all built into it. However, something you should note, if at any one point in time you can see a setting, say in the CLI on the radio, that you don't notice on cnMaestro, and that does happen. When we have a new feature released, we want to make certain that it works really, really well before it shows up in cnMaestro. You still have access to making that change. You can go into cnMaestro and you can go through an option where you can basically send the CLI commands to the APs, either in an AP group or in individual APs. And you can disable those commands or set them specifically as needed. Everything that's in the radio is in cnMaestro, if not through the GUI, through that option as well. Let me see here. Can I email you the slideshow? You'll be able to download that, as we mentioned. And let's see. I'm glad it was useful. Do you have recommendations for 2 or more floor buildings for placing AP? Cisco recommends basically directing on top of each other as any other common rule of thumb. I don't recommend on top of each other. It depends on the building. So the idea here is, let's say you have a 4-story hotel and you're placing APs in the hallways. You're limited on where you can put APs. See, that's always something to be considered. But you might have better penetration through the floor than you do through the walls. So if the APs can hear each other really well, that may not be a great thing because you're limiting your channel usage. You want to isolate APs from each other whenever you can, as much as you can. I would recommend staggering them somewhat. So let's say you had APs on the very ends of the hallways on floors 1, 3, and 5, and then the 2 and 4, they might be slightly in from each other. Then again, if the floor is built to material so that you get no penetration at all through it or very little, then just treat those as individual floors or as different buildings. So you're not really worried about it. It's good to do a test to see what kind of signal strength you can get through that. If you don't have a large number of APs, it's not going to matter because you have enough channels to separate them. But you're always better if you can isolate APs on the same channels from each other. Let's see, anything else? Oops. Some of your APs have Bluetooth radios in them. When will these be turned on? Or is there a way we can turn them on? It would be great for Bluetooth beacon asset tracking opportunities. I agree. So every serious vendor out there is putting Bluetooth in their radios now because of that. Bluetooth gives you all sorts of great tracking information. You can do some good locationing applications. You can run them across it. Why haven't we turned that on yet? Quite frankly, because there aren't enough applications out there to work with. It will be. We have the ability to turn it on pretty quickly as soon as we have a partnership with an ecosystem partner that does something with it. This is true for a lot of vendors out there. I think there's one out there today, Mist, that has they are doing something with their RF, with their Bluetooth today, but almost nobody else is. I can't tell you exactly when because I haven't seen a good application that is vendor neutral yet, and we haven't developed one ourselves. I wish I had a better answer for you, but right now the answer is sometime in the future. We expect to, we want to, we're talking to different players, but we don't have a good one defined yet. Sorry, that's not the best, that's not the most pleasant answer here, I'm sure. Oh, you're welcome. That was a thank you for the presentation. And what is cnMaestro? It is only available to registered retailers of Cambium. So for those of you new to Cambium, cnMaestro is our public clouds management system. It allows you to onboard devices, to manage them, to configure them, to troubleshoot, to create reports. It's in the public cloud. It's free to use. You can set up, you can go to cloud.cambiumnetworks.com, set up an account, and use that for almost anything that we sell today. Almost. There are a few products that are yet to be manageable through cnMaestro, but almost all of them are at this point. All of the Wi-Fi products are. You can also download the software and run it in your own virtual environment. So you can create your own private cloud. It's not necessary for operating any of our equipment, but it simplifies everything if you do. I highly recommend using it. There's no reason not to. There's no cost to using it. Is there a specifically designed AP for ceiling mounts as opposed to wall mounted? Yes, absolutely. Most of the APs, indoor APs, are ceiling mount. The E410, E400, the E600, those are all ceiling mount. The antenna patterns are such that they expect to be mounted horizontally, not vertically. So they're expect to be mounted on the ceiling, and they actually have built into the mount the ability to snap onto the T-rails that you have for when you have ceiling tiles. The wall plate AP, on the other hand, E430, that is meant to be mounted on the wall. So the antenna pattern is such that it expects to be mounted on the wall. It takes up the size of a single gang plate. We also have a dual gang mount that you can use, and we also sell a desk mount, so you can stick it on top of a desk. But the most common place to put that is mounted on the wall itself. The outdoor APs, however, have outdoor mounts meant to be mounted on a wall, on a pole. Lots of options for mounting, but you do want to orient the APs in the way that they're meant to be used. So the E410 and the 600s are meant to be oriented horizontally, the wall plate vertically. Okay. And that might be the last of it. Are there, let's see. I think that's everything. If I missed anything, please send in another question here. I think I got all of it. In which case, thank you very much for listening, and I hope this has been useful to everybody. Please definitely do look online to see what's there. It's not just this presentation, but others that we have done. And we will continue to do these, especially if there are any suggestions for what you guys would like to hear. We'd love to provide that information as well. Thank you very much.